design of microcontroller based PID controller and implement on a fourth order electronic process. So first we have to design a fourth order electronic process. 1 by s plus 1 to the power 4 we have to design. For that, let us consider this op amp. This is inverting terminal, non-inverting terminal. Let us ground this non-inverting terminal. Let us put one capacitor in the feedback, and parallel with that one resistor is in parallel. Input resistance is R. Feedback resistance also R. If you write KCL for this, the junction is V minus. Junction is V minus. For that, if you write KCL, current through this this path is V in minus V minus. This minus is suffix. V in minus V minus divided by R plus. This is incoming current. Here, V out. From V out, the incoming current is through this R is V in minus V out. This is V out minus V in divided by R, another incoming current. And the third incoming current is through this capacitor. That is d by dt of V out minus V minus. D by dt of V out minus V minus multiplied by C equal to 0. So the fourth current from this junction into the op amp is 0, negligible, because the input impedance of op amp is ideal op amp is infinity. Here it is very high. That's why this current can be negligible, approximately equal to 0. That's why only 3 currents, that is equal to 0. But for an op amp, V plus equal to V minus, we know. Already V plus is grounded, that's why V minus also at ground potential. This is also at virtual ground. That's why this V minus equal to 0. This V minus also equal to 0. This V minus also equal to 0. Therefore, V in by R, V out by R plus C into D, V out by dt equal to 0. Multiply on both sides by R, you will get V in plus V out plus RC dV out by dt equal to 0. Take Laplace transform, assuming 0 initial conditions, you will get this implies V in of S plus V out of S plus RCS, because for derivative S, V out of S, assuming 0 initial conditions. Therefore, you will get V in of S equal to minus V out multiplied by 1 plus RCS, or V out by V in equal to minus 1 by RCS plus 1. If RC equal to 1, that is equal to minus 1 by S plus 1. If RC equal to 1. Let us choose C equal to 1 microfarad, C equal to 1 microfarad, and R equal to 1 megohm. Therefore, RC equal to 1. So, if you select C equal to 1 microfarad and R equal to 1 megohm, then it's the transfer function is minus 1 by S plus 1. If you connect 4 such, if you cascade 4 such 1 by S plus 1, 1 by S plus 1 and 1 by S plus 1. If you connect 4 such op amp circuit in series, this is equal to, here you are giving plus, minus, plus, minus, plus. The output is plus. Therefore, G of S equal to 1 upon S plus 1 to the power 4. So that circuit will be connected here. This is Arduino. We are going to use Arduino as a PID controller. We are going to write program for this Arduino. Here, the output is PV, process variable. The fourth order system's output is process variable, that is connected into the channel A0, ADC channel A0. In addition to that, we have to give KC, TI, and we have to give set point. We have to adjust the manipulated variable in open loop. That's why we are using 3 parts. The part will be connected like this. Grounded, another end is +5. This is connected to A5. Like that, 3 parts are connected. A3, A4, A5. One for KC, another one for TI, another one for set point as well as manipulated variable. These are all input ports. These are all input ports. If you see the output, one digital output is to indicate whether it is in closed loop or open loop. One LED is connected here at the 12th pin. It is assigned as output port. If LED closed, it is in closed loop. That way we are going to write the program. So we are going to use the serial monitor already used in the lab to monitor what is happening inside that Arduino. One more switch is there. That switch will give 1. If you give 1 as input, the loop will be transferred from manual mode to auto mode. If you transfer to 0, it will come to open loop. So this is for bumpless transfer. So if you give 1, it will go to closed loop, 0 for open loop. Then the output of that Arduino is not a DAC output, it is pulse width modulated. That's why a voltage follower is used. RC circuit followed by a voltage follower. Voltage follower is used to get the output voltage. That is given as input to this 4th order process. That's all. The power supply. Regulated power supply is used to give +12, -12 and all, and the ground are required for this op-amp. That is given by regulated power supply. This is the experimental setup. Now we have to see the flow chart for that program. Initiate all variables, then configure all pins, whether it is input or output, and you have to configure the serial port. These are all done initially. Then whether you want to operate this in infinite loop. This is in infinite loop. This is in always loop equal to 1. That's why it is in infinite loop. Means if you turn on, always it will work as a PID controller. To select manual mode or here already I said, if you give 1 closed loop, 0 for open loop. This is in auto mode. This is in manual mode. So for that, that input is checked here. If it is yes, this part, these are all for closed loop operation. These are all for open loop operation. That's all. So if it is 1, it will execute these statements. If it is 0, then these will execute as open loop. Here, let us see first to open loop. The LED display connected number 12, that has to be turned off because it is in open loop. Open loop. That's why LED display equal to low. Then bias equal to 25. This is actually not given here. It will be given here. I corrected in the program, not in the flowchart. Bias equal to 25 or 35. As you wish, you can give. Then X1 is the output of the DAC. Here the pulse width modulated output. X1 equal to bias. That's all. Bias. Here one more statement is included. If change is greater than 10, then X1 equal to, this statement will be included here. X1 equal to bias. Bias already we defined 25. Bias plus 10. Otherwise, X1 equal to only bias. So that is one part already I told for you. For manipulated value, one part is there. If you adjust that part, if it exceeds 10, then it will add 10. Because if you adjust the part, what will happen? The voltage will increase like this. but we want to give step input. That's not possible with the help of part. That's why what we are doing is we'll increase whenever it exceeds the value 10, 0 to 255, we can vary. If it increases beyond 10 or 10%, we are checking for 10%. If it exceeds 10%, then we are adding 10% to the bias. So we are giving step input like this. So to make it as a step input, we are including these statements here. And we have to modify this flowchart in your observation notebook. Then set point equal to PV. Always we will make set point equal to PV, because at any time we may change from manual mode to auto mode. While changing from manual mode to auto mode, the set point must be equal to PV. That's why this statement. Then X1, its value is in numbers. Already I told you that 0 to 255 range, 0 to 255, that has to be converted into percentage for that one conversion statement. Then we have to display the values in the serial monitor. For that, we have to type PV, manipulated variable, KC, TI, and change. That is change. That is change in set point. For that, this change will be used, or to give manual value that exceeds 10, will add 10. For that, this change. These are the values will be displayed. Again and again, this will be this will be executed. If you change this port equal to 1, then it will come through this path. Here, LED display equal to high, we have to change, because we have to glow the LED because it is in closed loop. Then new set point equal to set point plus change. Already we gave some set point equal to manipulated variable. Already in manual mode we gave. Now we are in auto mode. Here, set point equal to new set point equal to new set point equal to set point. Already that is equal to manipulated variable. Plus whatever the change you gave, that can be included here. Change. Then error equal to new set point minus PV. Delta E equal to error plus past error. So to understand this, I have to explain position form and velocity form of PID controllers, that I will explain after this flowchart. So here we are executing that PI controller here. After that, the PID algorithm that I will explain after this. So this is the PI algorithm. After PI algorithm, X1 equal to M, that is controller output plus bias. So then what we are doing, then past error equal to present error, because next time when you come, this present error becomes past error. That's why past error equal to present error. Then convert the controller output into percentage, then write on the pulse width modulation, then display all values, then again and again repeatedly do this. That's all about the PID program. Now we have to see the velocity form and position form of algorithm, that we have to see. Position form and velocity form of PID, digital PID algorithm, digital PID controller. Digital PID controller. Here, E of t, you know, E of t equal to Y of t, that is output minus set point. That you know, E of t. What is E of k? E of k is in digital, that is Y of k, kth sampling instant minus set point at kth sampling instant. So this is in digital form. Digital. So controller output also in analog we will say M of t. Here M of k. M of k. Let us write first analog form. M of t equal to Kc multiplied by E of t plus Kc by Ti integral of E of t dt plus let us write for PID Kc Td dE by dt plus bias. So this is the analog controller output. But not E of T. E of K is what? K at kth sampling instant, the error equal to output at kth sampling instant minus set point at kth sampling instant. That is E of K. Now replace this in a digital form, then you will get M of K. M of K equal to Kc E of K plus Kc by Ti. This integration becomes summation. Summation means we have to multiply by sampling period T. The integration becomes summation of E of K plus Kc Td. dE by dt means change in error per unit time. dt is, let us approximate this dt is sampling period. dE means change in error, that is E of K minus E of K minus 1. Past error. This is present error. This is past error. Past error. The difference between the two is change in error, dE by dt. Therefore, we can write Kc Td multiplied by E of K minus E of K minus 1 divided by D. Instead of dt, we can put sampling period. This is approximated in digital domain. This is the digital position form of controller. Plus bias. Plus bias. This is position form of controller. Position form of controller. Here, this is total controller output. This is total controller output. So this can be written for delta M, change in M. Change in M means previous sampling period, what is the controller output? At present, what is the controller output? The difference between the two is change in controller output. If you know the change in controller output, we can add it to the previous controller output. Suppose previous controller output is 12 milliamps. At present change in controller output is 0.1 milliampere. Therefore, the new controller output is 12.1 milliampere. That's all. We have to add these two. That's all. If you add these two, you will get new controller output. Like that, we are going to find delta M of K. To find delta M of K, we have to find M of K minus 1. M of K is available. If you find M of K minus 1, the difference is delta M. So delta M equal to what? Delta M of K equal to M of K minus M of K minus 1. So what is M of K minus 1? From here we can write M of K minus 1. M of K minus 1 equal to what? M of K minus 1 equal to Kc multiplied by K minus 1 plus Kc by Ti multiplied by T, sum of here minus infinity to K. Here also minus infinity to K minus 1, because previous controller output E of K minus 1 plus Kc Td divided by T, E of K minus 1 minus E of K minus 2, because previous controller plus bias. So therefore, delta M of K means change in controller output equal to what? M of K minus M of K minus 1. If you subtract, if you from this, what you will get is, for first term, what you will get? Kc multiplied by E of K minus E of K minus 1. E of K minus E of K minus 1. Plus, if you consider this term and this term, what you will get is, up to K minus 1, if you subtract these two, up to K minus 1 getting cancelled. What is the remaining? What are the constant terms? Kc by Ti multiplied by T. Here up to K minus 1. Here up to K. The last term only is there. That's why E of K only. Plus Kc Td divided by T. And here if you subtract, E of K will be there. E of K will be there. E of K minus 1. Here also minus 2 E of K minus 1 plus E of K minus 2. That's all. This is the velocity form of PID controller. Velocity form of PID controller. What is the advantage? There is no integration. The integration becomes summation. No, that is removed. That's why no integral wind up problem will not be there. That is the advantage of velocity form. No integral wind up because no integration is there. Integration is removed. That's why you will get delta M. Delta M has to be added to previous controller output. That's all. That way it is written in this program. That's why here PI controller output is written like Kc multiplied by delta E. Delta E means what? Change in error. E of k minus 1 is called E of k minus 1 is called delta E. Delta E. T by Ti multiplied by T equal to 1 means that's why it is not here. Otherwise, here we have to include T multiplied by error. This is integral term. Integral term becomes E of k because summation goes off. So that is change in M. So x1 is previous value equal to M plus bias. M equal to M plus bias. We have to write one more statement. We'll see that in the program. This is the circuit. There are 4 stages of op-amps are there. 4 stages of op-amps are there. So it is 1 by s plus 1 to the power 4. 1 by s plus 1 to the power 4. This is serial monitor. Here, 3 parts are connected. 3 parts are connected such a way that we can adjust manipulated variable or set point. We can adjust Ti. We can adjust Kc. So this A0 here A0 is PV. Cross variable is given at A0. Here this output at 12th pin is port number I couldn't see here. Okay, 12th pin we connected to LED to say that whether it is in closed loop or open loop. The output of 10th pin, that is PMW output, is given to RC circuit. Already as I told, RC circuit, then it is given to voltage follower. So you will get DAC output that is given as input to this system. This is the arrangement. This is Arduino. This is Arduino. Arduino. That's all. Now we have to see the program to make it as an embedded system. So to write the program, first we have to declare the variables M, error equal to 0, past error also 0. The state, whether it is open loop or closed loop, to tell that state, bias, delta error. Delta error means change in error. Delta error equal to E of k minus E of k minus 1. That is delta error. Sampling period T equal to 1. PV cross variable. X1 is the controller output. Then set point, new set point, Kc, Ti, change for set point or manipulated variable, process variable, open loop, closed loop, to indicate whether it is 0 or 1. Based on that, LED will be cloned. That's all. So define LED as 12, ME as 10, bias equal to 25. Now I change it here. It is written outside. So always bias equal to 25. So a function call, void means it doesn't return anything. It is a function call to write the data on the serial port, serial monitor. That's all. Now we have to write the setup. The second pin is assigned as input. A0 analog input, A3 also analog input, A5 also another analog input, A4 also another. These 3 are for one manipulated variable, one for Ti, another one for Kc. And this is for PV. This is for PV. That 12th pin is digital output 0 or 1 to make the LED glow. This output is pulse width modulated output for to give the input to the 4th order process, 1 by s plus 1 to the power 4. Input is given here. Then baud rate is 9600. Then this is infinite loop. The loop always you have to put infinite loop. We have to put 1 inside, you know. Default 1 dana. Kc equal to, we are going to read that Kc, that part A5. In A5 we connected one part, you know. A5 we connected this part. So we have to read that Kc. So Kc equal to analog read A5. So we have to convert this into, if you read inside, it will be a 10-bit number. 0 to 1023 will be there. That's all. It is a 10-bit ADC. That's why this number you will get. To convert this into 0 to 10 scale, 0 to 10 scale we want to convert. That's why Kc divided by 1023 multiplied by 10. So Kc value, maximum value is 10, because for fourth order we know that 4 is the ultimate gain. That's why up to 4 is sufficient. So we gave up to 10. Ti equal to analog read another A4. Here we are reading, this is Ti, it is connected to A4. Here we are reading Ti. Again, you will get a number from 0 to 1023. That has to be converted into, that also 0 to 10 scale. That's why divided by 1023 multiplied by 10, you will get Ti Kc. If you want to give in the manual mode MV, you have to give, or if you in closed loop, you have to give set point change. For that, this A3 is used here. So A3 is red here. A3 is red here. A3 is red here. So that is also converted into scale 0 to 100, because set point range is 0 to 100. That's why the change equal to, after reading that, change equal to change it with 1023 multiplied by 100. So its range is 0 to 100%. So PV equal to analog read. Now we are reading the analog output. This output of this fourth order process is connected here. It is connected to A0. It is connected to A0. So we have to read that process variable. Process variable read analog read A0. PV equal to PV divided by again 1023, because 10-bit number. We are talking in terms of percentage. That's why multiplied by 100. So you will get PV in percentage. You will get 100%. Digital read 2. So here, whether it is in closed loop or open loop, we have to tell. That's why the switch is connected in pin number 2. So whether it is in ground, +5 or ground, we have to check. That is red here. So all inputs are red now. All inputs are red. It's over. State means whether it is open loop or closed loop. 0 means open loop. 1 means closed loop. That's all. Now, if state equal to low means what? Open loop. Open loop means we have to turn off the LED. So that LED means port number what? 12, I think so. Yes, 12th pin we are writing that output, that is equal to low. We are writing low. That's why LED will be turned off. If change is here, one more statement we have to write. X1 equal to bias. X1 equal to bias. If change is 10, I told. So if change is greater than 10, because if you change the part, the input will vary like this. Like this. We don't want like that. But we want a step change we want. To give a step change, if it increases the value of 10, how we are reading manipulated variable? 0 to 100%. We are reading this as 0 to 100%. Yes, change equal to change by 1020 multiply 100. So when it exceeds 10%, when it exceeds, if you change the part, when it exceeds 10%, when it exceeds 10%, the bias value will be added 10. So it will work like step input. At a particular instant, it will act like step input. For that, these three statements. If it is less than 10, the bias value, that is 25% alone will be given. 25%. This is equal to 25%. If you give change, if you increase that part beyond 10%, then 10 will be added. 10 will be added, but it should be executed only once. Otherwise, every time it will be added time. That's why we have to introduce one more variable here. One more variable here. what we can do, it should be executed only once. So let us introduce once equal to 0. Let us introduce outside once equal to 0. Before that state once equal to 0. Here you make within bracket once equal to 1. So if change equal to greater than 10 and once equal to 1. If the two conditions are satisfied, then it will go only once inside. Otherwise, if we come out again, once will become 0. That's why next time it will go. So m equal to 0, that is controller output is 0 because it is in manual mode. Manual mode, analytical controller output. This is analytical controller output. That is 0. Then we have to check for range. It should not exceed 100%. That's why x1, already we know that it is 35 only. If it should not be less than 0 or it should not be greater than 100. That's why this check before giving to pulse width modulation. So ensure that if it is greater than 100, make it 100. Less than 0, make it 0. Because some analytical works are doing here. That's why it may be out of this range. So after checking that, the controller output should be converted into 0 to 255, 8-bit. For that, again, we are dividing by 100 percentage. Is converted into 255. Then analog write MV equal to W. That's all. Again, set point equal to PV. Why in manual mode we are making set point equal to PV? In the PID controller, if you want to transfer from manual mode to auto mode, we will make set point equal to PV. Always we included this statement, means whenever it comes here, it will make set point equal to PV. If you transfer any time to closed loop, set point equal to PV. That's why this statement is there. That's all about open loop. In closed loop, this is closed loop. Else, after this, these two lines are there. Else, else, this is closed loop. This is for closed loop. Here, digital write LED high. So LED will glow to indicate that it is in closed loop. New set point equal to set point plus change. Before changing from manual mode to auto mode, make change equal to 0. Because we changed that to about 10%, so that it added 10%. Again, make it 0 before transferring from manual mode to auto mode. Change equal to 0. Because no set point change. That's why 0 will be added. Now set point equal to PV. Error equal to new set point minus PV. This will be 0. Error will be 0. That's why analytical controller output will be 0. So delta error means what? Already I told you that error minus past error. Now past error is 0. We initiated as 0. First time means past error is 0. Then we have to find the controller output. Controller output. Delta M we are using. Velocity form we are using. Delta M equal to what? Kc multiplied by delta E, that is change in error, plus T by T, that is sampling period. Kc is taken outside. Sampling period multiplied by Kc divided by Ta multiplied by error. That's why we are implementing P plus I controller. M plus equal to, it means what? M equal to M plus the analytical controller. Because M is delta M. Therefore, delta M equal to delta M previous controller output plus. That is the meaning. Now, this is assigned to the new variable x1. We are going to write, this x1 is used to write on the port. That's why x1 equal to M plus bias. We are adding the bias now. M is the controller output plus bias. So, past error equal to error. Because now present error is there. When it comes to next time, that will become past error. Again, we are going to check the range. If it is less than 0, make it 0. Greater than 100, make it 100. For that range check, that is always we have to write range check. After that, we will write the controller output on the output port. That is, it is in percentage. Again, we have to convert 0 to 255. That's why x1 divided by 100 multiplied by 255. Analog write. We are writing that analog write on the port. So Then we are going to print the values, that is set point, new set point, error, and all we are going to print. In addition, a function called data is there, that is also to print the values. I didn't copy that part. You know that. We'll type PV, KC, TI, and change. These are all will be typed in that data. Then a delay of 996, because to execute this only 4 seconds, 4 milliseconds, 4 milliseconds time only taken to execute all these statements. But we want, we have a sampling period of 1 second. That's why we are including a delay of 996 plus this delay for these statements. So 1 second delay means one sampling period equal to 1 second. Again and again, this will be executed. So you can implement the PID controller on Arduino board by using this program. That's all about. But in the lab, this fourth order process is fabricated on a PCB. That's why no need to give connections. Only thing is whether your program is working or not, that you have to check in the lab. That's all about this fifth experiment.